Hi everyone, we are going to do a latent heat example problem. And here goes. It is estimated that most elite athletes metabolize approximately 8,000 kilocalories or food calories every day. How much water would a person have to perspire or sweat off to metabolize this many calories or this much heat to dissipate from their body? And remember that human muscles are only about 25% efficient. So let's talk about this problem. If we're talking about an elite athlete, we're talking about people at the peak of performance. We're talking about Tour de France bicycle riders. We're talking about Olympic swimmers, things like that. So people who are just using massive amounts of calories to do some high performance sports. Now, how are we going to look at this? Well, this is the amount of energy that they are getting per day, that 8,000 kilocalories. Well, if we've got 8,000 kilocalories that a person is absorbing as food, kilocalories, as you know, is the same as 8,000 kilos times 10 to the third calories. So that ends up being 8 times 10 to the sixth calories of heat. Now, human muscles are only about 25% efficient. So what that means is 25% of this many calories makes a body move, and the other 75% actually goes towards heat, and that's heat that has to be removed from the human body. So 75% of that is going to be 6, because 3/4 of 8 is 6, times 10 to the 6th calories. So this is how much heat a person has to get rid of in the span of this day of very, very high extreme sports. So where does that heat, what does it get used for? Well, we're going to go back to that latent heat graph that we spent a lot of time with, and whenever I do a latent heat math problem, I go back to the graph. So we're going to look at this. Where does this start? Well, it's going to start with water. And as you all know, athletes need to hydrate, and that hydration is essential so they can keep their body cool. So body temperature is somewhere around 37 degrees Celsius. So let's start out and say that the water is now at 37 degrees Celsius. So the heat, this 6 million calories, has to be used to warm up the water up to that 100 degrees Celsius. And then the heat has to be used to vaporize it and sweat it away. Now, why do I go back to this graph? Because each segment of this graph is going to give me a fraction of my equation. During the up and down segment here, to warm the water that is going to be sweated away, we're going to use the equation Q is mc delta T, and during the horizontal section right here, this is the actual vaporizing of the water off the body. This is going to be quantity of heat is mass times latent heat of vaporization. So now we're going to construct our equation, and our equation is going to look like this. So the total heat is going to be used to warm the water, and it is going to be used to vaporize the water. Okay, the warm the water is this section of the graph, vaporize the water is this section of the graph, and the heat we have to work with is our 6 million calories. So let's put some numbers in here. The heat is 6 times 10 to the 6th calories, and I'm purposely going to work with calories because you can measure units of energy in calories or joules, and calories work just fine. To warm the water, this is going to be my equation. So mass of the water, specific heat of plain old ordinary water, and change in temp of the water. Plus, to vaporize the water, it's going to be this portion up here, mass of the water, specific heat, latent heat of vaporization. And latent heat of vaporization of water happens to be a number I know, so we're in good shape there. All right, now let's throw some numbers in here. We've got our 6 times 10 to the 6th calories. The mass of water, I'm going to just call mass because that's what we're solving for. Specific heat of water, if I stick to calories, is 1 calorie per gram degrees Celsius. The change in temperature, well, this is 137 up to 100. That's my change in temperature, and that's going to be 63 degrees. The mass of water is what I'm solving for, and the latent heat of vaporization of water is 540 calories per gram. All right, so 63 times 1, so this is going to be mass times Celsius is going to cancel, 63 calories per gram, plus mass times 540 calories per gram. And if I add those two together, I'm going to end up with mass times 603 calories per gram equal the 6 times 10 to the 6th. So the mass is going to be equal to 6 times 10 to the 6th calories divided by, I'm going to round that off because I like round numbers once in a while, 600 calories per gram. Calories will cancel, grams are going to come upstairs, and that's going to be right around 10,000 grams. Now the question is, how much water is that? Well, as you know from what we've talked about earlier, 1 gram of water has a volume just about at standard temperature and pressure of 1 milliliter. So we're talking about approximately 10,000 milliliters of water. And as you know, there are 1,000 milliliters in 1 liter. So we're talking right around 10 liters of water. Now, to give you an idea of how much one of these people are going to have to sweat in a day, can you visualize a 2-liter bottle of soda pop? This would represent 5 2-liter bottles of soda pop. This person is going to have to actually sweat away in the span of a day. It's more than 2.5 gallons of water they're going to have to perspire away in a day just to keep their body cool. That's why you shower after gym class. All right, you guys, we'll see you later.